So, hello everyone. Those of you who are here for the last talk may notice that I have the same accent and the same t-shirt as the previous speaker. This is a complete coincidence. Okay, so I'm going to talk to you about Java and Linux and their complicated relationship. There are two very important technologies that are kind of a matched pair. They go together a lot. We use them a lot. We have lots and lots of these instances running at LinkedIn. And most of the time they're just fine. They're all good, except when they're not. Then everything is a bit of a firework. So Java. Java is a portable application platform, in theory. An alternative way of looking at it is that Java is a system written for an imaginary OS which approximates the OS that it was on the set-top box that Java was originally designed for in the early 90s and bears only a vague relationship to today's modern operating systems such as Linux, Solaris, and Windows, where it's actually deployed. And most of the time this is just fine. Sometimes it's not. So I have 5 war stories. I will get through as many of these as I can today. And I'm going to give you the problem, what Java does wrong, and ways to mitigate it, battle tested by actual live application usage. So the first war story is garbage collection versus Unix virtual memory. So virtual memory is a very old Unix feature dating back to the late 70s. And what it basically does is it works around a feature of application programs called locality of reference, which basically means that some portions of an address space in a process are accessed a lot, and some of them are accessed very infrequently. And when you are a very clever operating system, you can work out which ones are which, and you can take the ones that aren't used frequently, shove them out to a slower medium like disk, and then save your precious kilobytes of RAM, because this is designed in the 70s. So Java behaves just like the programs that this feature is designed to support, right up to the point when GC happens. When you GC, there is a thread inside the Java process, and it walks over the entirety of the Java heap, which is in modern systems a multi-gigabyte virtually contiguous allocation of memory. And it reads and writes it because it's doing mark and sweep. So it marks things to these pages and then it reads them. And it does this once, twice. And portions of that happen, fewer and fewer these days, but still large portions of that happen while the application is stopped in a stop the world event, when the application is sitting there not doing anything, not proceeding, not responding to network requests, not doing anything useful. So this process of garbage collection needs to be fast, as in milliseconds fast, as in single digits of milliseconds fast if possible. However, if a large chunk of your Java heap has been swapped out to disk, a GC can take hundreds of seconds while I remind you that your services clients are not talking to you, they are waiting for your responses, they are timing out, your health checks are failing, your services, your instance has been kicked out of the cluster, latency spikes are propagating through the entire application, your SLAs are shot, basically an enormous day trip to Failtown. So here's a real world example pulled from our logs. This little guy went to sleep for 107 seconds in 2014. Not good. Why? So swap. Swap is slow. Really slow. There is a trope in the Linux community. If you're swapping out, you've already lost the battle. That's pretty much true. And there's a couple of good technical reasons for that. So swapping in, the process of swapping in, happens synchronously, seriously, one page at a time. Because it's basically the case of application does a page fault, kernel realizes, oh, I need that page, pulls that page from disk, then the application continues, half a microsecond later, it does another page fault, so you can see it's inherently a slow process. And also, the way that swap is laid out on disk doesn't have any of the tricks that are used by real file systems to be fast. So Because of the axis pattern, read ahead is basically impossible to do, and there is no attempt to save data into contiguous physical extents on disk like real file systems do today. So swap is just really, really, really slow. So how do we deal with it? Well, there's a few ways. The sensible and easy way is you just disable swap. Seems pretty simple. There's an easy way just to take it out of FS tab. You can check with swap on -s. There's a few problems with this. First of all, it affects every single one of your processors. Secondly, it's an OS-wide configuration change. Sometimes you run in an environment where they don't let you do that. So, there's a clever way. There's a well-known tunable called vm.swappiness. It turns out that if you set it to 0, the kernel makes a strong effort to not swap at all. Well, so the behavior of that depends on your kernel version. There was a silent, undocumented change to that behavior sometime in Linux's history in the last few years. So what it actually does on your kernel in your production system, And we tried it. For us, it just didn't work. It just went ahead and swapped anyway. So here's the horrible way of dealing with it. You have a Java heap, and you do a system call, mlocall, with this magical argument mcl current. What that does is that tells the kernel, walk through all the memory mappings that this process has at this moment, and mark them with a special magical flag that basically prevents them from being swapped out. And if you do this call at the right time, early enough in the process's lifetime, then you will mlock the Java heap, which exists by the time you're running Java code, but you will not mlock any of the other rubbish that happens in a Java process, like classes and strings and non-heap allocations done by libraries. So that's great. Unfortunately, mlocall has this behavior where unless you are root, or specifically you have the cap IPC lock capability, you get a resource limit whose default value is 64K, which is pretty much entirely useless. So you need to raise the resource limit. We found that the easiest way to do that was to add a line to this etc security limits.conf file, which is read by PAM during system startup and every time you log in, and controls the resource limits for processes. App here is the user that our application runs underneath. And so to check it works, there is a magical pseudo file, proc.pid status, and you can grep for certain things. So you want to look for the VM lock line. That needs to be non-zero. That tells you it succeeded, or at least greater than 64K. And you want to look for the VM swap line, which tells you how much of your application is actually out on swap. You want that to be very, very small. So in this case, we have a 32 gig, roughly, heap. And we have the entire heap plus about 7 gig of other junk locked into RAM, and a very, very small portion of this process swapped out. So, success. Okay, war story number 2. Sometimes you just need a file descriptor. Java hides the OS from you. And it does that so that you can write portable code, and also for reasons that can be best described as historical and commercial, it does it so that you can only write portable code. Sometimes you need to break around that and actually look at the underlying OS concepts. File descriptors in particular. So file descriptors, everybody should know by now, are these small integers that are used to name open files and sockets to Unix system calls, like my good friend Reed up there. And in Java, because it's portable, it tries to handle both the Unix style of file descriptors and the Windows style of file descriptors, which is a little bit different. And so it hides those details from you. So what my goal here was doing some detailed performance analysis on a network server that I own. And what I wanted to do was to look at the length of a socket's in-kernel input queue, which is a really, really easy thing to do. Here is a tiny bit of C code that does it. We use the phi-on-read ioctal, and that gives us a number in bytes. Very easy. In Java, well, Java wraps up a bunch of common ioctals for you in a very useful way. This is not one of them. So what we have to do is we have to basically convince Java to call ioctal itself, which is this complicated dance using the JNDI library. And we have to declare the actual ioctal's binary value, because this thing knows nothing about system header files. And then we just need to do the easy bit, which is, oh, I have a Java socket, I need to get a file descriptor. This is so easy. No. So there is a file descriptor object in Java which contains nothing but an int, which is the actual file descriptor that we want, but you cannot get at it. It is a private member. There are no accessors. And so how do we get that lovely little int out of there? Well, we have a number of ways. There is a well-known trick that you can Google using reflection. That's great, but I'm doing performance analysis. I don't want to stick a whole bunch of reflection code into my hot path. That's not good. There are tricks you could do using unsafe, which are well named. So the thing that I eventually dug up after a whole bunch of reading the JDK source code was sun.mis.shed sequence. I love this thing. This is where Sun hid all the ugliness of their model. It's basically the equivalent of lots and lots of C++ friend declarations between classes. It hides all the places where their class boundaries design doesn't match the reality of what you need to do within actual code. So it's very, very undocumented. Anyway, so there is a function in there that you can call that gives you a little object. That little object has two methods, one of which gets a Unix file descriptor, one of which gets a Windows file descriptor. One of them throws in, there are two instances of this class. One exists when you run this thing on Unix platforms, one exists when you run it on Windows. Obviously, one of them just throws an exception when you do the wrong one. Very, very simple. Let's use it. So this is what we do. This is a tiny little piece of code that took me a day of reading source code to work out how to get to, that you can use to just basically take an input stream, which is what you have in the Java world, and turn it into the little file descriptor that you need to actually call the little thing that you need to do in the first place, which was Octal. Why does Java make it so hard? Who knows? So my third war story is about NFS, big directories, and the pain you get when you mix these two up with Java. So the problem is this: we have a database backup system that takes dumps of MySQL stuff and then writes them into a directory on an NFS filer, a very expensive NFS filer. This directory, because somebody wrote the code this way, has thousands of files in it. And there's another Java process that wanders through this directory and does the equivalent of an ls-l, where it gets both the file names and some data about each of these files and just reports these. And that process was enormously slow. Why? Well, I need to deep dive into how NFS works. I used to be working on NFS, which is why I got called in to look at this. This is not my service that I own. So let's imagine that a process on an NFS client wants to read the contents of a directory. So it calls some libc wrapper that then calls the getDents system call. Then there is an NFS client code that lives in the kernel, and it sends a readdir RPC to the server and caches the result. So the readdir call looks like this. It takes an NFS file handle that represents the directory, and it takes a number of entries to return. And it returns you a list of effectively file names and something that's useless. Of course, there's a bit of complexity hidden here, but that's basically what it does. And so the message flow, so in this diagram, we have the application process on the left, we have the NFS client code in the kernel in the middle, and we have the NFS server on the right. So the left-hand arrows are local system calls. The right-hand arrows are network RPCs, which are probably 1,000 times higher. So when you do the ls-d, you get a single getDense call, which gives you a single read network RPC, which then returns you a bunch of file names. All very easy. So the problem with read is that it does not handle the ls-l case. Because in Linux file systems, the actual information, the inode information about each file is completely separate to the file names, and this thing doesn't return that. So let's say you want to do something like an ls-l, where you're printing out information about each file, not just its name. Your application then does a stat call to find out this information, a system call, and the Linux NFS client then needs to do some extra magic to the server. So this is what that looks like. So you do a getDense like before, that returns you the file names, then your application is doing a stat call, and that does a lookup RPC to the NFS server, which gets you the file handle, which lets you open the file, and it gets you the attributes, which lets you basically print out the length of the file, for example. And then it does that for the next file, and it's doing all of that serially synchronized on a single thread in the application. So you have, let's say you've got 1,000 files in your directory, you've got 1,000 RPCs, each one of them taking several milliseconds, done serially. Even though the client is, the kernel client is perfectly capable of doing 16 or 32 calls in parallel to the server, it's doing them serially. Needless to say, this is slow and bad. So NFS has another feature called read plus. And what that does is it bundles up all of that together into one call. And so you get a list of file names, but also attributes. Oh, this is the wrong diagram. So you basically just do a single read plus call, and you get back a list of file names and attributes all together in one big bundle. So that's great. So we should just use it. And forget that redo ever existed, except no, you can't do that because there is a secondary trade-off here that there is a protocol imposed upper limit on the encoded size of the results returned for any of these calls. And that's there because the server and the client are typically implemented in a kernel, and it's important to limit the amount of memory traffic that they do. And so if you have a read plus call, you're going to get more information about each file, but that takes up more space, so you get the results for fewer files in each call, which means if you have a large directory that takes many calls, you will take maybe 2 times, maybe 3 times as many read plus calls as you do readers. And if you don't actually want that information, if all you actually wanted to do, all your application was doing was just the LS model, where it only cares about file names, that's wasted and multiple times slower than it could be. So there's a trade-off. If you have large directories and you don't want the inode information, you want to do read. If you have larger directories and you do want the inode information, you want to do read plus. So there is, of course, no way for an application to tell the kernel what it's going to do. It just doesn't. But there is a heuristic that the kernel implements since about 2012, which detects which of these models your application is doing. And it works like this. Basically, when you do a getDense call, the first RPC sent to the server is always a read plus. After that, if your process does an open or a stat, it sets a magic flag on the directory, and if you do a subsequent getDense call and the flag is set, you keep using read plus, otherwise you fall back to read. So that gives us 2 optimal patterns, which are the things that all C programs do, which is you either do the LS model, which is getDense read plus, getDense read, or you do the ls-l, where you getDense read plus, and then a whole bunch of stat calls which come completely out of the client's cache and do no network traffic at all, and then you repeat that process. So let's look at Java. So This is the canonical way of listing a directory in the Java API. Availables are the only method available prior to Java 8. And what this does is, the important thing to look at is the second and third line here, which is dir.list files. And dir.list files is basically doing a sequence of getdents on the directory, reading the entire directory, slurping the whole thing up into a list of file names, which it then returns to you. Then you get to iterate over that list, and you get to do things like f.length. F.length will cause a stat call, which will then cause a call to the an RPC call to the server. And that's not fixable in this API, because the API is such that the return value of list files is a file array, so you have to return the whole thing. There's no other way to actually implement that API. So what this does when you actually run it is it does getdents, and because of the previously mentioned heuristics, that turns into readdir plus, then readdir. So we have cached the inode information for the first couple of dozen files, and then after that, we have no inode information. And so then we do some stats calls, and then a few dozen of them are cached, and then we reach the end of that, and then every stat call is a synchronous lookup call, RPC call to the server. So if you're reading a directory with a few thousand entries in it, this can be hundreds of times slower than the C program doing the same thing with its standard API. How do we cope with this? So there is a new API in Java 8 called java.nio.files. And you can create a thing called a directory stream, which is effectively an iterator that returns you a sequence of these path objects, which is just the same thing as the file object, except different, because why do it the same? And so this is effectively the same code. The difference here is that in the second and third line, we have done only an open of the file of the directory, not fetched any actual entries in getdents, and then the iterator in the for loop, the hidden iterator next call that happens there, is actually calling through libc and doing a getdents when it needs to on demand, which means that our system calls are interleaved in the C pattern, and we trick the heuristic into thinking that we're doing the right thing, and this performs at the same level as speed as C. So there is this interesting little nugget that I found in the Java 8 documentation, which says that the new directory stream function may be more responsive when talking with remote directories. May be more responsive. It's 1,000 times slower. Okay. War story number 4, GC, log hard with a vengeance. So, Java GC is an important thing. It's a limiting factor on the availability of Java services. In production, so that means that in production, it's really, really important for us to keep that GC behavior working well. And because you can't manage what you can't measure, that means we have to measure it. And so we enable GC logging in production. And when we enable it, I mean we enable it very, very thoroughly. We have all the options because more data is better. So this is an example, don't try to read that, of what happens when a major GC event happens, the kind of log that you get. So that's about 1,200 bytes of information. When there are various minor GC events, you get smaller messages that are about 200 bytes. I looked on some of our production servers, and a lightly loaded machine is logging about 39,000 lines a day. That's 3.4 meg. And a heavily loaded machine is logging 543,000 lines in our log file a day. 33 meg a day. So that's a lot of logging. Now the problem is this. The GC log unlike every other log in your system, is written from Java's C code during stop the world in the GC code. And it's doing a write system call. There is no user space buffering. So every line in that file is a write system call, which is an opportunity for the kernel to block while you're in stop the world. So if the root disk is heavily loaded, let's say, for example, you have a system process that's writing 300 meg of some tarball, because that happens in production, you can get a long tail latency in the single digits of seconds very easily for writing a single line of data to your log file. And if this happens in your stop the world, you now have a stop the world latency of 1 to 5 seconds, while your clients are timing out because their timeouts are small. So what do? We could disable GC logging, and then we have no idea what's going on. We are flying completely blind. So no thanks. There is a really neat thing that some people suggest at this point, which is log4j, async logging. That doesn't help us. This is written from Z code. There was an idea that was tried when this was implemented in LinkedIn, not by me, I should point out, which is to log to a named FIFO. This is a really good idea, except if the process at the other end of the FIFO dies, then your writer gets blocked, which means your application is blocked and you are in a much worse state than you were before. So this is what we do. We log to a file that's mounted on a fuse file system. Why? Because the semantics of fuse are that if the reader process, the process that implements the file system, if that process dies, then the write call to that file will fail immediately with an error, which means that the application will be a little bit upset, but it will not block and it will keep going. And you'll lose logs. That's unfortunate, but the application will still keep running. So that's pretty awesome. Okay, war story number 5. DNS lookup. It's easy, right? So Java has a bunch of really easy APIs to let you look up hostnames. You can actually plug them into one of the constructors on the socket class, or you can use the connect call, and you can just give it a hostname and a port, and it goes away and looks all that stuff up for you and makes it all magic happen. It's really easy, very fun. Let's peel that onion for a moment. And all of those easy APIs, all those APIs that are very easy for you to use, are just layers and layers of wrappers around this little guy, which is inetaddress.getAllByName. And what that does by default is it calls libc's getAddressInfo, which calls out to a daemon that lives on your box called nscd. nscd is a piece of awesome. It's part of the glibc distribution. It's basically completely standard and runs locally on pretty much every Linux box on the planet. Some people disable it. I have no idea why. It's configurable. It has multiple name service providers, in particular a DNS client. Everybody understands this thing and how it works. And most importantly, it understands and obeys time to live that comes back from DNS queries. So if your DNS server is telling you this record has a 3600 second time to live, 3601 seconds after you query in SCD and you query it again, that record will be gone and it will actually talk to the DNS server. So, what about Java? So, the inetaddress class conveniently caches the results of lookups for you in RAM, in process, for 30 seconds, exactly. There may have been a TTL that the DNS server gave you, whatever, Java doesn't care. So the annoying thing is there is actually an API in sufficiently recent versions of glibc 2.8 and above called getHostnameByName get host by name 3_r, which will tell you the TTL. It's obscure, there isn't a man page for it, but it's there. So why does Java do this? Well, the Java documentation and the comments in the source code have some unconvincing mumbo-jumbo about security problems. Personally, I think DNS is one gigantic security problem, and caching it badly is not going to be a solution for that. Nevertheless, that's their official reason. I think the real reason, and this is actually a good reason, is that it is enormously faster, and that hides application problems where applications are resolving host names too many times for no good reason. So I did a little bit of timing. Java in-process cache takes about 50 odd microseconds. Talking out of process to NSCD on your local box, it's about 70 milliseconds. I was surprised by how high that number is. I'd expected it to be sub 10. I'm surprised. I don't know why that is. I can't explain it. DNS server, obviously this depends on your infrastructure. For us, it's about 200 milliseconds. So if you have an application and your application is doing lots and lots of host name resolving, the Java cache is actually a significant performance advantage. And I think that's the real reason why they do it. So there's a problem. If you have DNS records which have a long TTL, and most of them do, most of the ones that are actually like stable C names and such like have a TTL in the order of a day or an hour, then talking out to NSCD every 30 seconds for something that you know or should know prima facie is not going to change for the next hour is just a waste of time. There's a worse problem. Let's say you have gone to the other end of the spectrum and you have a very, very short TTL coming back from DNS. And there are good and valid reasons for doing this. Let's say you're doing round robin DNS for load balancing, and you're trying to also do it for failover so that you have some clever system at the back which basically pulls stuff out of the round robin results when a system fails. So you want a very short TTL to minimize the amount of time in which clients will see a host that has failed. We actually have a very clever piece of machinery in LinkedIn that does something very similar. So let's say you have like a 3-second TTL, which is what our machinery does. And Java is caching your results for 30 seconds. So this means that for 27 seconds after your data is now invalid, it's telling you the same thing despite that being potentially wrong, which means if you have a failover, you don't get a 3-second failover, you get a 30-second failover, which is much, much, much worse. So how do we deal with this little horror? Well, the obvious way is to just disable the software cache. There is a security property that you can set. It's actually 2 of them, which have exactly the same effect. The big problem with this is it's global to the host, or more specifically to the JRE install. There are some other ways to set that security property. They are more complicated. Sometimes you have to write some Java code to do that. But that's still global to your JDK process. And if you have other code in a library, buried deep in a library, that is also doing DNS resolving, that process's times and latencies are going to be affected. And that could be a problem. So there is, of course, a way to do it using reflection. Reflection is almost never the correct answer for questions, unless, of course, the question is, what do vampires regret most? This is my favorite, by which I mean least worst option for this, which is to call the JNDI library in Java, which is an interface to naming systems. It has a DNS client in there, and with a few calls, which are actually documented, you can look them up, you can actually do your own DNS calls directly, so you're talking directly to the server. The big problem with this, of course, is that you are bypassing NSCD entirely. In some cases, that may be the right thing to do. The good thing is, it only affects your code. It doesn't have global impact through your process. And for the super Jedi mind trick version of this, you can actually get serve records from your DNS. If it supports that, our clever machinery that does that will give you serve records as well. And that lets you do client-side load balancing. The downside is JNDI does not really support serve responses. It will give them to you, the plain text that came out of the DNS off the wire, and you've got to parse that string. That's a bit of a pain. And you've also got to deal with the fact that you may have stale entries left over from hosts that have failed, and you have to cope with that. Okay. So I'm getting near the end, and I just want to recap and go over some lessons that I learned. So you've probably heard of this joke before. What are the two hardest things in computer science? Naming, cache invalidations, and off-by-one errors. I want to propose a fourth, making Java behave rationally. More seriously, Java is not magic. You need to understand that Java does not always do the right thing for your OS. The mere existence of an API that is convenient doesn't mean it's doing the right thing or even a sane thing. Horrible things live in the corners. This little darling is a ladybird spider, which I didn't even know existed yesterday. Modern software is complicated and has ugly, ugly corner cases where horrible things live. This is normal and we should cope with it. And finally, and this is something that I have to tell Java programmers a lot, portable code is nice, working code is better. So you have to do what's needful, and you have to not be afraid to subvert the bondage and discipline mindset of Java's portability dictates. And finally, you have to know your OS and how you're interacting with it. And that's me. Questions? I believe we have a mic. Everybody's stunned into silence, or just waiting for lunch. I know, I'm looking forward to lunch. Question? Or no, you're just saying lunch. Yeah.
So no questions for Greg?
Oh.
If you do, please approach that mic.
I think we should declare it lunch. I think we should declare lunch.